So first of all, let's talk about what an antiderivative is. I think before we start finding them, we should have a good idea of what they are. And before that, I'm going to kind of review what we did with derivatives, right? Now, when we did derivatives, we started with an original function, right? So I called it the OG function. Okay, and usually we called it like f, right? From now on, I'm going to call the original function with a big F. Okay, so big F represents my original function. Okay, I watched this video and I thought it was just an Australian thing, but I think it's actually just normal. I think people actually call this a primitive. Okay, I'm sure, I think that's worldwide actually. I was watching this Australian guy explain it and I wasn't sure if it was just him or if it was everyone. I think everyone calls it a primitive, okay? Then what we did with this original function is we took the derivative, okay? So we did the derivative and then we ended up at, well, the derivative, right? So this is the first derivative of our function. Okay, and ways that we show that is either, we usually use the prime notation, but for this class right now, I'm going to call this little f. Okay, so little f is the derivative of big F. Okay, now what antiderivatives are is we're actually going to start from the first derivative and we're going to go backwards. Okay, so an antiderivative is the opposite of a derivative. We start with the first derivative and we go backwards and find the original function. So this is an antiderivative. Okay, so what we're actually doing is we're working in the opposite direction of how we were going before. Okay, technically, we can call a function big F an antiderivative of my derivative little f. Don't worry about on an interval. If the derivative of big F is little f for everything in that interval. Okay, so that's the technical definition of the antiderivative. I like to think of it as this diagram up above. I think it makes a little bit more sense to me. All right, so example one, this is a very classic antiderivative question. Okay, we are going to find the antiderivative of x squared. Okay, now when we think about this, in our minds, we're going to ask ourselves this question. Okay, we're going to think about what function has the derivative of x squared. Okay, and let me write that out real quick, just so we're all on the same page. We're going to ask ourselves if we can find a function, okay, whose derivative is x squared. Okay. Okay, so any function that has a derivative that ends up being x squared. Any guesses on what that function might be, Sam?
1/3 times x to the third.
1/3 times x to the third. That's a good one, right? And how can we check to see if that is the antiderivative of x squared? Yeah, right. I can check, right? So let's just check real quick. Okay, if I take the derivative of this, it would be 1/3 times 3, and then using the power rule, that it would be x squared. So it looks like the derivative of this function is x squared. 1/3 x cubed is a derivative of my function x squared. So using the technical notation, big F, or my antiderivative, is 1/3 x cubed. Okay, any questions so far? Yeah. Ooh, okay, so you're wondering about where that, I think a lot of people have heard about the plus c. Let's talk about that. Okay, can someone give me another function whose derivative is x squared?
1/3 x squared plus 1.
1/3 x cubed plus 1, right? How about this one? F of x equals 1/3 x cubed plus 1. Well, let's check to see if that has a derivative of x squared. Okay, so if I took the derivative of this, it would be 1/3 times 3 x squared, and then the derivative of 1 is just 0, right? So the derivative of this function is also x squared. What's another function that's the antiderivative of x squared? Michael?
Plus like
Plus 5, right? I can do anything, right? I can add any constant number to 1/3 x cubed, like plus 5 plus 16 minus 2000, and I would still get a function whose derivative is x squared, okay? So it looks like there are multiple antiderivatives of x squared, and they kind of all have the same form, which is what Sam was saying. Let me kind of generalize this, okay? So in general, okay, the antiderivative of my function is f of x equals, well, it's always going to be 1/3 x cubed plus or minus some sort of constant, right? I can always add a constant to this because the derivative of a constant is always just 0, right? So I'm going to say that as plus c, where c is some sort of constant number, okay? Okay. And if we take a look at all the graphs of these antiderivatives, so 1/3 x cubed, 1/3 x cubed plus 1 plus 5 plus 3, we can graph all of those antiderivatives. They're all to the third power, so they have that disco man shape. But if I add something to the function, it's just going to shift up and down, right? So any sort of vertical shift of my original antiderivative is going to be also an antiderivative of my function. Any questions on how I got the antiderivative or anything like that? Okay, now we'll talk about a more general way to do the antiderivative. So if you were a little confused how we got from x squared to 1/3 x cubed, we'll talk about a more systematic way to do that. Okay, but for now, let's just think about going backwards and then adding a constant to whatever we get. All right, let's flip our page and do a few more of these. Okay, so we have a theorem, okay? And it's not really a theorem, it's more of a definition, okay? If we have an antiderivative, big F, right? Big F represents our antiderivative. We call this a general antiderivative. Well, there's many different types of antiderivatives, plus 5, plus 1, plus 0. Anything plus c is a general antiderivative. So that's what I mean when I say that. Okay. Well, let's go through a few of these and see if we can work our way backwards, and then we'll kind of piece everything together so we have a good idea of how to find any antiderivative. All right. So let's go backwards. All right, let's do part A here. Okay, I want to find the antiderivative of sine. So I want to find what function has a derivative that is sine. All right, any ideas?
Negative cosine of x plus c.
Perfect, good. So you actually put everything together here. So Jude said negative cosine x plus c. Why is cosine negative?
Because the derivative of cosine is negative sine.
Yeah, the derivative of cosine is negative sine. So in order to kind of counteract that, we need a negative up front, okay? And we'll talk about a way to kind of generalize this. So if you're a little confused getting there, don't worry yet. But why don't we just kind of check, okay? Okay, we can take the derivative of this function. The derivative, well, the negative stays there. The derivative of cosine is negative sine, okay? And the derivative of any constant c is 0. Okay, so the negatives cancel out, and it looks like the derivative is sine. So it looks like I actually found a function whose derivative is sine x. Okay, now it is very important that we put the plus c there, because if we don't, then we actually miss a bunch of functions whose antiderivative or whose derivative is sine. Okay, so make sure we always tack on that plus c there. All right. Any questions on part A? Let's move on to part B.
You have multiple antiderivatives, not just like plus c, but multiple things that result in the same.
I'm pretty sure antiderivatives are pretty, I think it's just one. I think you only get one. I'm trying to think of any. I'm pretty sure there's only one antiderivative per derivative. Yeah. Yeah, that's a good question though. All right, let's do 1 over x. Okay, can someone give me a function whose derivative is 1 over x?
Natural law.
Natural log, right? The derivative of natural log of x. Let me write this in blue. I don't know why. The derivative of natural log of x is 1 over x. Okay. Now there is something I do kind of want to talk about with this one. Oh, what am I forgetting when I write ln of x plus c? Good. Okay, and the derivative of ln of x is 1 over x. Now this one's actually a little bit tricky. And the reason it's tricky is because of the idea of domains here. Okay, so before we go on, let me just ask you, what's the domain of 1 over x?
Zero, and then from 0 to infinity.
Perfect. So negative infinity to 0, 0 to infinity. Basically, we can't have 0 there, right? So 0 can't be, gosh, 0 cannot be in the domain of 1 over x. All right, let's talk about ln of x plus c. What x values can I plug into ln of x?
0 to infinity.
0 to infinity, and am I including 0?
No.
No, right? So we can only plug positive things into ln of x, okay? Okay, well, I have an antiderivative and a derivative, and their domains don't match, okay? Now, this is where things get a little bit tricky, okay? Going from ln of x plus c to 1 over x, I basically take the derivative to get from ln of x to 1 over x, okay? But the problem here is I can only plug in positive numbers to ln of x. So saying that the derivative is 1 over x when, the domain of the derivative is more than what I can plug into the original function is kind of weird, okay? So to counteract this, what we're actually going to do is not say that the derivative of ln of x or 1 over x is ln of x plus c, but we're going to say that the derivative of 1 over x is actually this, the natural log of the absolute value of x plus c. Okay. Now let's talk about the domain of this one here. What's the domain of the natural log of the absolute value of x? Perfect. Negative infinity to 0 and 0 to infinity, right? I can plug in negative values into this because if I plug in, say, -2, I'm going to get +2 and I can take the natural log of that, okay? So what I've done is I kind of changed this function to expand the domain of my original function so that when I go from the original function to my derivative, I have the same domain. So I can plug in the same amount of numbers, okay? So 1 over x is kind of special here. The derivative of ln of x is 1 over x, but going from 1 over x to the antiderivative, we do have to put an absolute value sign here. So this one's kind of special, okay? All right, any questions on the natural log or 1 over x? All right, why don't we try x to the 5th? Can someone give me a function whose derivative is x to the 5th?
X to the 6th power divided by 6 plus c.
Perfect. X to the 6th power divided by 6 plus c. Good. And if you're ever confused about this, we can go and check. Okay. The derivative of x to the 6 over 6 is 1/6 times 6 times x to the 5th. The derivative of c is 0. The 6's cancel out and we're left with x to the 5th plus 0. That looks like we're right. Okay, so we did find a function whose derivative is x to the 5th. Okay, so this is my derivative here. Okay. Now, some of you are pretty good with going from a power function to its derivative, but I kind of want to make this a little bit more systematic so we're not trying to struggle. Okay, what number is my antiderivative of any power? And the way we're going to do that is I'm going to ask you what the antiderivative of x to any power is. So I want to know the antiderivative of x to the n power. Of course, n not equaling -1 because that's the natural log derivative. Okay. To do that, why don't we just plug in some values for n and see what can happen? Okay. All right. let's make n equal 1. Okay, if n equals 1, we want to find the antiderivative of x to the first power. Okay, well, what do you think a function is whose derivative is x to the first power? Well, if the answer is 1, is the derivative of 1 x to the first power? What's the derivative of 1?
0.
0, right? So the derivative of 1 is definitely not x to the first power.
Oh, it's, or no, 1/2 x squared.
Good, 1/2 x squared, right? Because, okay, we can check, right? But if I took the derivative of 1/2 x squared, I can do 1/2 times 2 times x to the first. The 2's cancel out and we're left with x to the first. So we're all good. All right. Let's make n equals 2. Okay. So that means we're trying to find the derivative, or sorry, we're trying to find the antiderivative of x squared. Okay. Can someone tell me a function whose derivative is x squared? Zach. Oh. Zach.
Yeah, I was gonna say 1/3 x cubed.
1/3 x cubed. Perfect. All right. What about n equals 3? We want to find a function whose derivative is x cubed. David.
4x fourth.
Perfect, right? Okay. Why don't we do this? Huh? Oh shoot, I forgot plus c. This is bad. This is bad. I'm installing bad habits to you. Good, thanks. Okay. Why don't we do this? If f of x is x to the nth power, okay, what do you think the derivative of x to the n is?
X to the n plus 1 power divided by n plus 1 plus c.
Perfect. X to the n plus 1, right? So we're adding 1 to the power. We're dividing by the power plus 1, and we also have to add the c to it. Okay, so this is in general a rule. It's kind of like the opposite of the power rule, right? So it's how to go backwards from the power rule. We just add 1 instead of subtract 1, and instead of multiply, we divide. Okay. Any questions on example 3? Okay, now I promise we will put this together, but I do want to kind of get us a little bit in the thinking mindset before we start thinking about memorizing. So why don't we try examples? You know, I think I'm gonna let you try these ones. So why don't you try example 4a and b? B is a little bit harder, but I think we'll get through it. But Michael, do you have a question? Oh, all right. Let's try these on our own. Let me give you like 3 minutes to work on this and then we'll come back. Oh, wait. What was your question?
What do you do when n equals -1?
Okay, let me talk about this. So when n equals -1, we have x to the negative first power, right? Which is 1/x. If I want to find the derivative or the antiderivative of 1/x, didn't we kind of do that in example B? Yeah, so the derivative of this is the natural log of the absolute value of x plus c. Okay. All right, I know some of you are still working, and if this is slightly confusing right now, I promise you will get easier. I do just want you to get into the thinking mindset of, okay, how do I construct these antiderivatives before I tell you to start memorizing? Because I think it makes it's a little bit easier if you just kind of think about it first before I tell you all the rules. So let's just go through part A, okay? This time we have a bunch of things being added together. Antiderivatives work the same way as derivatives, where if I add things or subtract things together, you're just taking the derivative of each piece and kind of piecing them back together, okay? So let's take this piece by piece here. Right now we have x cubed, okay? What's the antiderivative of just the x cubed portion? Mm-hmm. 1/4 x to the 4th. Good. So that's using the power rule that we just did in example 3, right? So just the derivative of x cubed is 1/4 x to the 4th. Okay. Now we're going to subtract off a 2x. Okay, so I'm just going to do -2. What's the derivative or the antiderivative of x?
Actually, I just had that as x squared instead of having a 2 there at all,
Oh, okay.
like negative x squared.
So it's x squared over 2, right? But then you canceled out the 2's. So that's why you just had an x squared.
Well, and then the derivative of x squared is just 2x.
Oh, okay, I see. So you did the whole thing in your head. That's fine. I want to show kind of all the steps here, but that's totally fine if you want to do that. Yeah, you got it. What's the derivative of just x though? Or the antiderivative, sorry. Ooh.
1/2 x squared.
1/2 x squared, good. So 2 times 1/2 x squared, okay. And then there's one I didn't tell you about yet. What's the derivative of 1? Or I keep saying derivative, I'm so sorry. What's the antiderivative of 1? You had it. 1x, right? So a function whose derivative is 1 is literally just x, right? The derivative of x is 1. So the antiderivative of 1 is x, okay? Now remember, you have to tack on that plus c because there's multiple antiderivatives, not just one. But this is our general antiderivative. Now cleaning this up, it looks like I can cross out the 2's here. So if I wanted to write this a little bit more neat, I'd have x to the 4th over 4 minus x squared plus x plus c. Okay. Any questions on part A? All right, let's move down to part B, which I think was a little bit harder. Okay. Now, whenever we do antiderivatives, we're going to do the same thing with derivatives. Whenever we see like a power in the denominator, I always like rewriting the power in terms of a negative power. So instead of writing 3 over a to the 4th, I like writing 3a to the negative 4th. Okay. Now, I'm not going to do it with the 2 over a. Any guesses on why I'm not changing 2 over a to 2a to the negative 1? Yeah, right. The power rule in the reverse direction, that doesn't work for like 2 over x, right? 2 over a is going to use the ln rule. So I'm going to leave that one alone, but I changed the first one, okay? And I'm going to leave the 4a squared there. Okay, so let's do the antiderivative of each piece here. How can I find the antiderivative of 3a to the negative 4? Well, it'll be 3, right? What would I multiply 3 by?
Maybe 1/3.
1, would it be 1/3 or negative 1/3?
Negative 1/3.
Negative 1/3, right? And what would the new power be? Would it be the third or the negative third? Negative third, right? So I know I kind of did this really fast. Let me just show an extra step here. What I did here is I just did the power rule, but we have negative numbers, okay? So the power rule says the antiderivative of a to the negative any or a to the any power is by adding 1 to the power. So I did negative 4 plus 1, and I divided it by negative 4 plus 1. Okay, so that's how I got the negative 3's there. Any questions on the negative power? Okay. What's the derivative of negative 2 over a?
Natural log of x, natural log of the absolute value of it.
Perfect, but then the 2 comes up front too, right? So negative 2, natural log of the absolute value of a. Remember, in part B in the last page, whenever we're taking the derivative of 1 over x, we have to put absolute value so we conserve that domain going from the derivative or the antiderivative to the derivative. Okay. Okay, next we have 4a squared. Can someone tell me the antiderivative of 4a squared?
4a cubed divided by 3.
Perfect. 4a cubed divided by 3. And what did I forget when I wrote this antiderivative? Plus C, perfect. All right, let me just clean this up here. It looks like the threes end up canceling out. So I'm left with negative, a to the negative third power is 1 over a cubed, okay? Minus 2 natural log of the absolute value of a plus 4/3 a cubed plus c. And that looks like it's my final answer. All right.
Would that stay negative? The,
Which one?
I'm looking at 1 over a cubed. Just wondering why that's negative.
Oh, because this one's up in the numerator. I switched it to the denominator. So when you go from a power up top to the bottom, that power goes to the negative value.
No, I'm talking about the negative font.
Oh, this negative came from here. So that negative just stayed the same. Yeah, why don't we check to see if this is right? And I think it will make things a little bit more clear here. Okay, now I didn't leave much space for myself to check my answer. But whenever we're confused, we can always just check to see if our answer is correct. Okay, so how do we check to see if our answer is right? Yeah, find the derivative of my answer and hopefully they match up with what the question said, right? So what's the derivative of negative 1 over a cubed? Now we're thinking in the forward direction. It's a little bit hard. Well, a cubed is a to the negative 3. So this would be negative 3 a to the negative 4th power, right? Okay. The derivative of 2 natural log of a would be 2 over a. Okay. The derivative of 4/3 a cubed would be 4/3 3a squared. And the derivative of c is 0. And if you clean that up, you'll see that it matches the original function. So it looks like we did the right thing at the end. Okay. Any questions on part B? Okay. Now what we're going to do is we're going to piece this all together. I think it's easier to do antiderivatives when we kind of have a chart that kind of pieces everything that we know all at once. So why don't we go ahead and do that? And then I think it makes it a little bit easier to be able to find derivatives of everything. All right, so if we go to the next page, what we're going to do is we're going to go through a few rules, okay? We're going to find, we're going to take a function, the derivative, and we're going to find the antiderivative of each of these two functions, or each of these functions on this chart, okay? Now, before we go on, I just want to remind everybody that we have a derivative that we represent with f, and the antiderivative is the original function, right? So the original function we call capital F, right? So we take the derivative to go from capital F to F. We take the antiderivative to go from lowercase f to uppercase f. Okay. So let's say I wanted to find the antiderivative of some sort of multiple, so 2, 4, 6, c times the derivative f, okay? What do you think the antiderivative would be? Yeah, c times big F of x, okay? So any constant multiplied by a function, it kind of just gets multiplied through. So you don't have to worry about multiples of something. Also, for the first two, don't worry about plus c. These are kind of just general rules, okay? All right, we kind of talked about this in the last example, but let's say we have two functions being added together. What do you think the antiderivative of f of x plus g of x would be?
F of x
Uh-huh.
plus capital G of x.
Perfect. The antiderivative of f plus the antiderivative of g. Now we just did that in the last example, right? We had a bunch of things added together and we just took the antiderivative of each piece and added those antiderivatives together, okay? So these are kind of just general rules. Okay, the third rule is kind of like the reverse power rule. So remember, this is analogous to the power rule. Remember, we want to find the derivative of x to any power as long as that power isn't -1 because that's the ln one. Can someone remind me what the power rule said? Perfect. Okay, so that's something that we use for the powers. Okay. Someone tell me what the antiderivative of 1 over x is. Perfect. ln of the absolute value of x plus c. Okay, we did that in part B of our first example. What do you think the antiderivative of e to the x is going to be?
Yes.
Perfect. E to the x plus c, right? Remember, the derivative of e to the x is e to the x, so it goes the same way the other way. Okay. The next one's kind of hard to think about. Let's say I wanted to find the antiderivative of b to the x.
It's not B to the X.
It has to do with b to the x, and it does have a plus c, but there's something that we got to multiply b to the x by. Yeah.
X or B.
Okay, so when we did the derivative of b to the x, it did involve the natural log of b, and we multiplied it. What do you think we're going to do if we're finding 1 over, what did you say?
1 over B.
Not 1 over b, but
1 over X.
not x. Okay, let's go backwards. So the derivative of b to the x, does anyone remember what the derivative of b to the x is? Cool. Okay, so this time we multiplied. What do you think we're going to do if we're finding the antiderivative?
Natural log of X.
But, oh, you mean like it's in the denominator?
Yeah.
Yep, we're just dividing. Okay, so remember, the opposite of multiplication is division. So we're literally just doing the same thing, but we're dividing this time. Okay.
You care about domains at all?
This
You know,
time
just
the
a constant.
yeah, this time it doesn't matter because b isn't like x or anything. It's just a constant. That's a good question though. All right. Let's keep going. Cosine. What do you think the antiderivative of cosine is? Sine. Perfect. Remember, the derivative of sine is cosine, so going backwards the same way. We talked about this briefly. What's the derivative or the antiderivative of sine? Negative cosine of x. All right. Now I would go on, but I think it's about quiz time. I do want to give you some time to work on that. So what we'll do next class, we're going to pick up on this. We'll finish the rest of the antiderivatives, and then, yeah, we'll pick up from there.